Oh, 2.
Ignore that.
Okay.
You lost your other marks. Right there. Okay, let's take a look at this. What happens when I put in 1 to this function?
Which function? Sorry.
X squared plus 10 over, so I have 11 over 7, right?
11 cents.
What happens when I put 10 into that function? Or sorry, 2 into that function. 14 over 10. 5 into that function. 35 over 31. Plug 10 into that function. I have 110 over 106. Put 50 into that function. I have 2,510 divided by 2,506. 100 into that function, I have 10,010 divided by 10,006. 1,000, I have 100,016, or sorry, 1,016,000 over 1,000,006. What do you notice about the 10 and the 6 in this?
They're constant.
They are, but do they really matter after a certain point?
Not really.
Okay. Do I not have enough zeros there?
Isn't it 10,016?
Yeah, that's a 60.
It's
Everything else is only 4.
why is it 16?
Oh, yeah.
No, it's supposed to be 10. That is supposed to be 10.
It is a 10?
Yeah. Now, again, what number is this approaching as we start to put in larger and larger values into that function? As x gets larger, what is the y value getting closer and closer to? We have 1,010, or sorry, 1,010,000 divided by 1,000,006. What is that approximately? What is that approximately? 1,010,000 divided by 1,000,006. Really? What's 1,000,000 divided by 1,000,000?
1.
So 1,010,000 divided by 1,000,006 would be approximately 1. Yeah, it's going to be
0, 0, 0, 0,
exactly.
0, 0, 0, 0, 0, 4.
So I'm more worried about what it is approaching, right? So as we're getting out here, we're starting to see that we're getting closer and closer to the line y is equal to 1. And we can see something similar because this is an even function. So it's an even function, so it is symmetrical about the y-axis. We would see something if I plugged in negative values for this. Okay. Now, what do we call that line? Y is equal to 1? What type of horizontal? What type of horizontal asymptote? A horizontal asymptote. Okay. So as we're getting here, we're getting the number approaches 1. Okay. So our notation for this, as x gets larger, as x gets to infinity, the limit of this function is equal to 1. And here, as x approaches negative infinity, the limit of this function is also equal to 1. So we know we have a horizontal asymptote. Now, a horizontal asymptote is what is happening as the graph approaches the extremes, the negative infinity, the positive infinity. There are lots of times where we do cross over a horizontal asymptote. These are all examples of the different types of systems you could have with a horizontal asymptote. It could cross the asymptote, but we don't really care because we're more worried about what's happening out here. Right? So as the asymptote or as the x values get large, what is happening to the graph? We don't care about it crossing the asymptote at this point. So a horizontal asymptote is a little bit different than a vertical asymptote. Vertical asymptote, we get closer and closer, but never touch. Horizontal asymptotes, as x gets larger or much more, like larger or larger negative, it is approaching that point and never touching, but it may have touched earlier on. Like this one would be. Okay.
Whoa.
Look at the extremes. What is happening as x gets really large or really negative? Okay. So this would be what we're talking about here, a normal horizontal asymptote. It does not cross the axis, right? It gets, as we get out to the extremes, we end up with x's approach, or the limit of the function as x gets larger approaches to whatever L is in this case.
So it crosses the asymptote.
Okay. Again, we're only looking at, when we talk about a horizontal asymptote, what is happening at the extreme ends of the graph, right? The really, really negative large numbers or the really, really large positive numbers. Here, this is an example of one where it does cross at this point here. But the asymptote is out here where we're looking at it. So here, as the limit, as x approaches infinity, is whatever L is. Yeah, it does cross at this point, but we don't know what that, we don't care about that point. We only care about the extreme. This one, what's that? No, we're not. This would not be talked about a limit. We would just say, okay, where is the function equal to 1? Well, at this point, it's equal to 1. Like we could plug 1 in and solve it if we wanted. We're not usually going to find that. We only really want to find our x-intercepts and our y-intercepts. Okay.
What's the definition of an asymptote?
Okay. So a vertical asymptote is a line it gets closer and closer to but does not touch vertically. A horizontal asymptote is more defined of a line as x gets larger that it approaches but does not touch. So do we have asymptotes up here? You're looking for it? Don't go asymptote definition up there. Okay.
Never mind, I can't read that one.
Which one?
I'm
going, I can read them all, and I'm blind. Integral notation.
No, like what does it say on?
Closed is with the square bracket, and open is with the parentheses. Now, here's one that's really going to make your head hurt.
Why?
It's bouncing up and down.
So you're telling me that sine has a vertical asymptote?
This is not a sine function. Or this may be a sine function, but not a sine that we're talking about before, right? We can talk about different ones that might look like that, but I have no idea what that function would be. Yes.
So with that one, where is it like getting closer but not reaching?
So somewhere out here, this line would be kind of flattening off, okay? So what is happening? It's approaching that value. In this case, it might be approaching it from both, like it does kind of, you see how the bumps
Yeah.
get smaller and smaller? It is approaching one from different sides. We're going to basically say, we're not going to really worry about this guy.
Thank
Nice.
God.
Okay? He's a very, very interesting function. I've never found one that we work with that has two different asymptotes either. It has a positive asymptote. This one has an asymptote as x gets into the positives, and it has a different asymptote as x gets into the negatives. I've never found one. I'm not saying there isn't one, obviously. There's this one here, but it's not something that we're going to work with. Our basic ones will have one horizontal asymptote. Usually it might be crossed once like this guy or that guy, but we're looking at the extreme ends of the function.
What does that function look like? Like, what
This
is
one?
it? Yeah.
I really off the top of my head, I've seen a few like this. What's that?
That'd be sine that Sean said, or x and power 12.
It'd be more likely a sine with some type of operation done on it. Don't try the operations because there's so many.
What about like the middle one? Like the bottom low one?
This
What would
one
that
here?
Be like?
That could just be a rational function that has a maximum. So there's another, say there's a vertical asymptote here. This guy's going down here, but then the maximum rises above where the horizontal asymptote is. So we only care about what's happening on the extreme, though. Focus on that. Okay, so here's the thing. We are going to use these two guys in a lot of different ways. Okay, what happens here as the limit as x approaches positive infinity? What's going to happen to this function as I start to plug in larger and larger numbers? Let's say this is y x to the 1 over x squared. Okay, so plug in 1, it's 1. Plug in 2, it's 1/4. I plug in 3, it's 1/9. I plug in 100. 100 is 1 over 1 million, which is essentially 0.000001. Many zeros in that one. But it's essentially 0. So the limit as a function like this approaches infinity, doesn't matter what the exponent is there. It can be 1, 2, 64, etc. 1/2 for that matter. Okay, as x approaches infinity, we're talking about 1 over a large number. 1 over a large number becomes close to 0. So this limit is 0. Okay? Now, depending upon what that value is, that might get there quicker. But if you have the limit as x approaches infinity of a large number, that reduces down to be 0. We can replace that with 0. The same thing with negative infinity. Okay? It might be approaching it from the negative side, but it is going to get closer and closer to 0. Now, this does help us to do this. Now, I can look at this one and I know that the horizontal asymptote in this one is 3 over 5. We talked about that in Math 30-1 because we hadn't talked about limits. I can take this function here. If I multiply every... What's the question, Marissa?
Oh, I'm a little stressed about this. This doesn't seem fun.
Really easy, Marissa. Now, let's show you how I get this without, because again, I've done this a lot. So I want to take a look at this and how do I do it, or how do I know this without doing a lot of work? Well, can you multiply the top guy by 1 over x squared and also multiply the bottom by 1 over x squared?
I could, but I'm not.
Okay, so when you multiply by 1 over x squared over 1 over x squared, what are you multiplying by?
X squared over X squared. No,
Which is?
never. 1.
Thank you. Am I changing that function by multiplying by 1.
No, wait.
So, what's 3x squared times 1 over x squared? What's 3x
3x
squared?
squared over x squared, so 3x. Right?
Think about that again. 3x squared divided by x squared.
I regret it, I'm sorry.
3x squared divided by x squared. We end up with 3x squared over x squared minus x over x squared minus 2 over x squared over 5 over x. Now, I'm going to skip this step a lot, but now, I don't really want to write this out. I'm going to do it in this case. Our property of our limits can say that this is going to be the limit as x approaches infinity of 3 minus the limit as x approaches infinity of 1 over x minus the limit as x approaches infinity of 2 over x squared.
Whoa.
Okay, property of limits, going back right to the start. The limit of a subtraction can be written as the subtraction of all the limits. Okay? The limit of a division can be written as the division of the limits. So, again, am I going to write this down all that often? No. But I want to show you what happens, where all this information comes from. Sean, limit as x approaches infinity of 3.
3.
Nice.
Limit as x approaches infinity of 1 over x. 80.
0.
Right? As this x gets bigger and bigger, this number gets closer and closer to 0. So I can replace this entire thing with 0. 2, the limit of x approaches infinity of 2 over x squared. Okay, again, just getting bigger quicker, but again, minus 0. So those two terms disappear to 0. The same thing down here. The limit as x approaches infinity of 5 is just 5 because nothing changes.
So we get 3 over.
And that's what I said earlier. So what we're doing here is we're looking at our ideas of limits. And okay, what happens if I divide everything by the largest power in that expression? In this case, it was x squared. And then what happens as that limit goes forth? Now, then you can do this by just looking at it. It's an x squared over an x squared. Everything else disappears, and we have 3. The coefficients would be 3/5, right? So that's going back to what we had in Math 30-1, where we had no idea or did not talk about limits. But that's all limit is what happens as x gets really big.
So x approaches infinity. 3/5.
So that function, the limit of this guy as x approaches infinity is 3 over 5. And it's also negative because it happens to be, it's not an even function, but it would also be negative in that case. If it was x approaching negative infinity. Sorry? Well, I know I'm going to have a couple vertical asymptotes somewhere. and I'm going to have a horizontal asymptote here.
That's what we saw.
We found the horizontal asymptote. We maybe not in here, but what's happening out here,
That's why I was very confused over it.
we know that it's going to be some, I don't know, it's going to be something like that at the extremes there. We could then find what's happening here and what's happening here, and so forth. So we're finding the horizontal asymptote. That's all we're doing. What's the largest power in this one?
One.
Large, okay.
Is that wrong? Never
It
mind.
is right, because we have square root of 2x squared. Well, that's just going to be, right? Now, what I'm going to do here is I'm going to divide every term on the top by x squared, because the square root of x squared is x, right? And I'm going to divide every term down here by x. So now I end up with the limit as x approaches infinity of the square root of 2 plus 1 over x squared over 3 minus 5 over x. Now, what happens as I plug a large number into those for x's?
0.
Where?
Oh.
Be more specific. 1 over x squared is the limit of 1 over x squared as x approaches infinity is 0. The limit of 5 over x as x approaches infinity is 0. So I end up with square root 2 minus 0 over 3 minus 0. Square root 2 over 3 is my horizontal asymptote. This is my, or actually this is the limit as x approaches infinity of this function. And it also gives us our horizontal asymptote. Sorry? Okay, do this one for me. What is this limit? Now notice this one's different. The degrees are different. What's the largest degree of that function? 10. Oh. Limit as x approaches infinity of 3x cubed over x to the fifth minus 5x over x to the fifth. Tidying that up a little bit, we end up with 3 over x squared minus 5 over x to the fifth over 2 minus 2 over x to the fourth. What happens as I plug in my large number to my infinity? What happens to that term? 0 minus 0 over 2 minus 0, 0 over 2.
So it's not.
So X on the bottom is going to be smaller.
Hmm?
Remember it not?
Why did the other one use two different?
Yeah.
Okay, so this one here, we still used, we multiplied this guy by 1 over x. Because we have a square root, if I just multiply by 1 over x, I can't get that in there, right? So I had to multiply by 1 over x, the square root of 1 over x squared, so I could do my multiplication with my radical signs. Right? We cannot multiply a whole number into a radical sign. We have to square it with the square root sign, then you can multiply, right? So here in both cases, these are both 1 over x. This is just written in a different form. This one here, the largest degree is x to the 5th. What do we end up with? We have a horizontal asymptote at y is equal to 0. So this limit is 0, and we have a horizontal asymptote at 0. Think back to math 30. We have a lower degree over a higher degree. Where was our horizontal asymptote all the time in that case? Y is equal to 0.
Oh.
So let's look at one more.
Yeah, there's degrees.
Yeah, agreed. It's difficulty too. Why not?
Yes, that's the reason you make when you realize that.
You just did.
Yeah.
I did not know.
You just don't want to do it.
Yeah.
Okay, so let's look at this one.
Holy crap.
No,
I'm good.
Now, we should know where, oops,
I literally
yeah.
have to take pictures.
Now, the top, I'm going to multiply by 1 over x to the 4th. Okay, because what does this guy work out to be? The degree down here is going to be x to the 5 halves, which is smaller than x to the 4th, right? So I'm going to take this, I'm going to multiply this guy by 1 over x to the 8, which is the same as 1 over, where is it? Is 1 over x to the 4th, and the square root of 1 over x to the
This is a lot of information.
16. Not 8, 16. Okay? Are they the same?
Oh, okay.
So I end up with the limit as x approaches infinity of 3 plus 5 over x cubed divided by the square root of 4 over x to the 11th minus 5 over x to the 16th. That, plug it in. 3 plus 0 divided by the square root of 0 plus 0. Does that make sense? So what's 3 divided by the square root of 0? Undefined. This does not have a horizontal asymptote, okay, because it's undefined. Now we also described that we had x to the 4 over x to the 5 halves, higher degree on top than on the bottom. Math 30, we always said, no, that doesn't have an asymptote. This might have what's called a slant asymptote, which we will talk about later. But there's only 3 options for this. You have a horizontal asymptote at y is equal to 0. You have a horizontal asymptote at y is equal to some number other than 0. Which is easy because we can figure that out, right?
Wait a second. Can you repeat the first two?
So he'd equal everything.
Yeah.
Yeah.
So then why do you say it just steps? I'm just saying it.
3 steps.
And there's a third option, no horizontal asymptote, or a slant asymptote. So let's look at this function here. Okay.
Yeah, or a slant asymptote. But
Okay, Marissa,
what?
I want to find the horizontal asymptote.
Ah.
Okay, so limit x approaches
Right.
infinity. Now, if I say determine and not state, you best show me some work.
Oh.
So we end up with so this becomes the limit as x approaches 0, or infinity, I should say, of 1 plus 4 over x plus 3 over x squared divided by 2 plus 5 over x minus 3 over x squared. 1 plus 0 plus 0, 2 plus 0 plus 0. So, as Marissa stated, I don't have problems with her answer, but it will be described as determined. Show me how you got there. Okay,
I freaking nailed that one.
all right. Dylan, if I want to get the vertical asymptotes for this function, what is required of me? So I'm going to need to factor the bottom. Two numbers that multiply to -6 and add to 5. I'm going to factor the top also. Doesn't really matter. Well, actually, you're going to need it right away. X plus 3, x plus 1. Now I know I'm going to have a 2 somewhere. So because that's negative, I'm going to put a positive 3 here and a minus 1 there. And I'm going to check to make sure. We have 2x squared, positive 6x, minus x gives me my minus 5, and I have my minus 3. So basically what you want to do is factor that for your x-intercepts and your vertical asymptote. Do I get to, oh, we have one more thing too.
Cross off x plus 3.
Okay.
Sorry.
So we have reduced. How many vertical asymptotes do I have? How many factors do I have left on the bottom? How many vertical asymptotes do I have?
No.
So our vertical asymptote, is x is equal to 1/2. We have a point of discontinuity at x is equal to -3. And I'm going to plug -3 into there. I end up with -2 over -7. So I have point of discontinuity is -3 and 2/7 for y.
Not just a guy you crossed off.
Yes. Because I can't plug -3 into here. It's not a vertical asymptote because it's being removed. So there's a point of discontinuity at that point. And Dylan, where is our x-intercept?
Negative.
X-intercept is going to be -1, 0. One last piece of information that's easy to find. What is our vertical, or what's our y-intercept? It's going to be 3 over -3. So our y-intercept will be 0, -1. So we've got a lot of information from that. We can kind of sketch this now, or at least get some understanding of what we've got. We've got a horizontal asymptote at 1/2. So y equals 1/2. We have a vertical asymptote at x is equal to 1/2. We have a x-intercept over here at -1, 0, and a y-intercept down here at 0, -1. Okay. And we also have the point -3 and 2/7, which would be somewhere out here, an open dot. Can you guess the left-hand lobe of this? What's it going to look like?
Yeah.
It's probably going to look a little bit like that. We don't have as much information here. How could we get that? Where is it increasing? Where is it decreasing? Okay. In this case is what we have, right? We don't have all the information, but just with this, which basically did everything new that we really did with this one, this is all Math 30. I'm going to guess it looks like this, but I could be wrong. I would have to have that function decreasing throughout the entire system.
Is there ever a downside?
If there's a domain restriction, yes. Right? If I have like this one, not that one. This one here, there's going to be, or there could be a domain restriction because of this. There isn't actually in this case, but there could be because of the square root sign. So they're saying, oh, it can't have less than that number there. So then you would have a one side of the graph. Any questions about that?
Why?
Why?
Yeah, why?
Why what?
It's a lot of work. For one thing.
Yeah, that's basically what it is. Okay. A lot of the stuff that we're doing here is allowing you to mentally figure out, okay, that solution makes sense or it doesn't make sense, as the case may be. Now, it's not cold in here.
No.
It's so cold here.
It's a nice temperature. Yeah, it's a good temperature.
Okay, so the notation here. Now this one happens, what happens if you have a, where you don't have a vertical asymptote or horizontal asymptote? You have one of those that I call slant asymptotes. So here we're just basically saying the limit as x gets bigger, the function also gets bigger. Okay, so that's all we're saying here. In this case, that means our left hand or our right hand, or in this case, that would mean we have some type of a notation up there. It's just going up. Okay, and then the other ones here as x, that would be down here, that second one, and over here. Right, so all we're saying with this notation is as x gets larger, so does the function. Now, there are some limitations to this. I don't know, I cannot treat this, like there are, as I said, there's properties of limits. Right, when we're approaching a certain number, we can just make, like this guy, if this was approaching 4, I could just say the limit as x approaches 4 of x to the 4th minus the limit of x approaches 4 of x. That cannot work when you have infinity here. This is not the case. Okay? All right, well, let's talk about this. What's x to the 4th? As x approaches infinity, what's infinity to the power of 4?
4
Infinity. I don't know, it's an infinity. What's x as x approaches infinity of x? What's that? Infinity. So what does this mean? Which infinity is bigger? Well, in this case it is. But in all the cases, is that going to be the case? No. So we cannot use this. Okay? This does not work. This one does. When you take that and you have to factor. Okay? So this one can be factored out relatively easy, right? Okay? Well, how is this one the same as that one?
Raised to the power of infinity.
But how is this function? Forget the limit. How is this function the same as that function? I've taken out a common factor of x. Okay. Now, this does work. I can take my multiplication property. I can take my multiplication property. This is infinity. This is infinity.
Double infinity.
What's infinity times infinity?
Infinity squared.
A bigger infinity, right? Because there's no such thing as infinity squared, but it's a bigger infinity. Therefore, we do know that this is the case. Okay? So, adding and subtracting doesn't work as x approaches infinity or negative infinity, but the multiplication and division principle does, although the division principle makes my head hurt. That's why we don't tend to do this with a rational. We would tend to do it with what we were doing before, the limit as x approaches infinity, and do divide out by the x squareds. So here we have a polynomial. Forget what are the x and the y intercepts of what's the okay? What is the x intercepts of this function?
-1. I'm really scared I'm going to get it wrong. -4. And that one would be 3.
What's the y intercept, Sean?
Ah.
How do you get the y intercept?
You're correct.
So we have 4 squared, 16 times 1 times 3. So we have 48. All I did. Now we want to figure out the end behaviors. We kind of know the end behaviors, but it's kind of hidden here. So we're going to do the limit as x approaches infinity of x plus 4 squared times x plus 1 times 3 minus x. Okay. So, what happens if I plug infinity into this? I get another version of infinity. What happens when I plug infinity into this guy? I get a version of infinity. What happens when I plug infinity to this one?
Right on negative.
I end up with a version of negative infinity. So this works out to be a really big negative infinity.
Why?
Negative times positive times positive. So we're down here as x gets bigger and bigger. What happens when x gets larger or gets to be a larger and larger negative number? So let's just change this to a negative. So what's this going to be? Negative infinity squared.
Positive.
Okay, so that'd still be positive infinity. Here, negative infinity. That's going to plug in negative infinity here. We're going to get a negative infinity. I plug in a negative infinity here. What do I get? 3 minus a negative number. So I end up with a positive. So now I have positive, negative, positive. Sorry, positive, negative, negative. What do I end up with? I still have a negative infinity. Okay. Now let's talk about what happens at the 0 and negative 4. Does it cross? Turn around? It bounces. So we're bounce down here somewhere, up to cross 48, down there.
Square.
Because of the squared here. If it's an even degree exponent on a factor, you have the line tangent to that. If it's a third degree or fifth degree, what does it do?
It should look like it should be like
You have a point of inflection at that. Oh,
It's a sketch.
you gotta call that a sketch because mine is terrible.
gold squares.
Okay, this is, okay, you guys have, or certain individuals in here have made this much more difficult than it requires to be. Okay? So you have 6 questions. It says determine, Marissa. It does not state. It does not say state. So determine means show me how you got there. No, they are not synonyms in mathematics. They are different.